As a continuation of our study of Newton's method, take a look at the equation sine of x equals x over 3 and ask, is this an equation that can be solved by hand? And I think very quickly you'll see that we have the same problem we've seen in some other examples where there's an x here and an x here, and if we solve for one of them, say solve for this one, we get x equals, but there's still an x remaining on the right-hand side. And so we can't actually hone in on x. And if we start playing more challenging games by maybe doing our inverse sine function of both sides, that can help the left-hand side, but it doesn't help the right-hand side. Here I can tidy up the left and get x equals something, but that something still has an x in it as well. And so we're back to where we started, where we simply can't find the x coordinate. Does that mean there's no solution? Absolutely not. If we sketch these graphs, let's take sine of x, pi over 2 is around 1.6. We're trying to draw this to scale. Let's make that 1, and that's 1. So at pi over 2, we're at our peak. So the sine graph looks like this. And we'll do the same thing on this side, like so. And the graph of, let's label that. The other part of this is x over 3, and that's over 1 up a third. So about here, we can draw that line and also draw it to the negative side. So this would be the graph of y equals x over 3. And from that, there's actually one answer that pops right out. Hey, x equals 0. Double check. 0 equals sine of 0. Yep, sine of 0 is 0. So x equals 0 is an easy solution. However, there's another solution hiding over here. And if we continued the graph onto this side, there would be another solution over here in the negative territory as well. So it looks like there's at least 3 solutions from this sketch, two of which are not the kind of thing we can solve for by hand. The x equals 0 we do have exact, but these two need more work. Where will that point be? Well, in the sketch here, it looks like it's maybe 2-ish or 2.5, somewhere in that range before it hits down at pi. So 2 is probably not a bad starting place. So let's try that method that we just introduced, where we have our x estimates. We'll start at 2. And we'll apply the technique. Remember, the first step is to redefine our equation, though, so everything that's interesting is on one side and the right-hand side equals 0. Then we can define that whole entire left-hand side as our function f of x. Once we've done that, we can create the derivative just by taking the derivative in a normal fashion. And the derivative of sine is cos, and we end up with negative 1/3 for that next derivative. Again, as soon as we do the derivative calculations, we're assuming everything's in radians. The sketch we drew assumed everything was in radians, so be careful with that in this kind of numerical method when you're using your calculator a lot. The ingredients that we need for Newton's method are the function value and its derivative. So now we can plug in those values into here. Sine of 2 minus 2/3 is 0.243. We'll keep 3 digits here. Cos of 2 minus 1/3 is negative 0.749. Now our next x is the old x minus the function value divided by the derivative value. So we take 2 minus this over this, and that gives us a little bit to the right, a new x value of 2.324. That becomes our new guess, and we repeat the calculations. We take that and plug it into our function. We get a value of negative 0.045, so getting close to 0, remembering that's our target. We want our function value to be close to 0, and a slope of negative 1.017. With these ingredients, we can evaluate the Newton's method formula and get a new x, and we get now 2.279, or if we round, 2.80. Let's do one more step. Taking that 2.8, putting into the function value and into the derivative. We end up with a quite small value here, 10 to the minus third, and a slope of negative 0.85. Doing the last update calculation, we'll take that as our old value, run it through this calculation here, and we get 2.279 this time. So it sounds like 2.279 is going to get us very close to the right answer. Just to confirm, we'll plug it into our function value. We seem to have converged here. We're not getting much change as we go from step to step. So what we'll do is take this last value and plug it into our equation to confirm it's close to the right answer. Our original equation was sine of x equals x over 3. And we're checking that 2.279 is approximately a solution. And how do we confirm that? Well, we take the sine, which is the left-hand side of our equation. There it is. The sine of 2.279. That gives us a value of 0.7595. While the right-hand side, which is 2.279 over 3, gives us a value of 0.7596, 7 if we round. The key thing being, of course, that these are very close to equal to one another, and that combined, the fact that those are close to each other confirms that x equals 2.279 is very close to a solution. We saw some other ones to the equation, to the sine x equals x over 3. And so again, we've demonstrated with an equation that we cannot solve by hand, we can still obtain a fairly accurate estimate with a bit of legwork to start, and then applying Newton's method to improve that initial estimate to as high an accuracy answer as we need.